I'm going to start by going over an evaluation of the ground motion models that we're going to be using for the Palo Verde site, and then I'll be talking about our approach for the median. Okay, so for our candidate GMPEs, there are two main requirements for the GMPEs in this area. And the first is that they have to be applicable or valid for the lower magnitude range. And this is important because we're comparing with data in this range, so the models need to work in the low magnitude area. And they also need to be applicable to large ground motions. We're using events from the NGA West 2 database. These events are located far away, distances 200 to 400 kilometers, and these are the events that, well, this distance range is what's important for the hazard calculations as well. So this is just a summary of the different ground motion models that have been considered. And basically for our area, for the Palo Verde site, there are 4 models that are applicable to this region that they're both valid within the low magnitude range and then the higher magnitude range at large distance. So we'll be evaluating the Abraham's or ASK model, BSSA, CB, and CY. Okay, this is the logic tree that Bob showed this morning, and okay, I'm gonna have feedback. Oh, okay. All right, so we're looking at the data set. We have the NGA West 2 for strike slip in California. The distance range we care about is greater than 6.3 and distances 200 to 400 kilometers. From that data set, we're going to use the methodology that Nico explained yesterday, and we're going to generate then 1,000 different models, and from those 1,000 models, we'll pick 10 different representative models to use as our base case. And then on this other branch here, we have alternative data sets that will be selected by the NGA West 2 developers.
Yeah, I just wanted to point out, Katie's we don't have the Salmons maps for this one yet, so you're going to see Salmons maps for Diablo Canyon tomorrow. She's going to then focus on the rest of this model.
Thanks. Okay, so I'm going to start by providing an update of the study that Jenny Watson-Lamprey gave in January at the January workshop. And so what she did, we wanted to see if there was a difference in the attenuation between earthquakes in the northern region and earthquakes in the southern region. So this is the Palo Verde site right here. And these pluses, I guess, are stations from the mobile array. And the concern was that there's an area of lower attenuation here in the south as you go down into the Salton Trough, or the Gulf of California. So what Jenny did is she separated these earthquakes, here are the earthquakes, into basically 3 regions. She separated them into a northern region, there we go, and then a southern region down here, and then the earthquakes in the middle were kind of in a transition zone. And she wanted to see if there were differences in attenuation between the earthquakes, attenuation in the path between the earthquakes to the north, to the Palo Verde site, and the earthquakes from the south to the Palo Verde site. And when she did this study in January, she was using the Chu and Young's model. So since then, she's updated it, looking at the attenuation and comparing it with all 4 of the candidate models. So these 9 stations are the stations she focused on here. And then Palo Verde is right here, kind of behind this middle station. So there's the northern region that she chose, and this is the southern region, and the region in between was kind of the transition zone. And ultimately what we're trying to do here is to develop a path term then for the northern region. It's an average path term, and then an average path term for the southern region. And this is just to show what branch on the logic tree we're working on. So this is that combined source and path term that Bob talked about this morning. Okay, so for the median models for Palo Verde, there are two key issues. The first is the distance attenuation, which I talked a little bit about, and I'm going to show Jenny's results. But her conclusion from January was that no change was necessary to the NGA West 2 models to account for this attenuation. And we'll see that that conclusion still holds after she's compared them to all of the different GMPEs. And then there is the large magnitude scaling. So the scaling from about magnitude 6.5 to 8.5. And like I mentioned, we're going to be generating 1,000 models using the methodology the salmon methodology that Nico was talking about. And the 4 models that we're putting into this are just the 4 that have passed for Palo Verdes, so the 4 NGAs minus Idris. And then the range will come from the 1,000 models, the range of the 1,000 models. Okay, these are the earthquakes that Jenny looked at. I'll just let you glance at that for a second. The largest magnitude is a 7.5, and I think the smallest is a low 4, like a 4.2 or something. Okay, so this dark circle shows the earthquakes in the north she looked at. So there's a cluster of 3 earthquakes here, an earthquake here, an earthquake here, and an earthquake here. So in the next few slides, what I'll be showing then are the earthquakes from the NGA West 2 data set, and also the earthquakes, these earthquakes from the NGA West 2 data set, and also recorded then at these stations. So recorded on California stations and recorded on this mobile array. So the California stations will show up in blue, and the mobile array stations will show up in red. And then she's comparing them with the different NGA models to see if there's a difference in the attenuation for the northern region. Okay, so these are the ones recorded on California stations, and then these are the earthquakes recorded in Arizona. The data has been corrected for VS30, and Jenny, what, 500? Okay, so to a VS30 of 500. And then the GMPE models have been, oh, sorry, that's it, right? Something was done to
The GMPs are adjusted by the event term.
Oh, right, the event terms. Okay, and then only the GMPEs that there were event terms for are shown. So if on one of the plots you don't see a GMPE, it's because there was no event term. And so the main point of these figures then is that the models are fitting both the data, both the earthquakes as recorded in California and in Arizona very well. So I think, let's see, these are different periods. This is 0.2 seconds. This is 0.5 seconds. This is 1 second. And here we have 2 seconds. Okay, and then this earthquake, it was magnitude 5.06. Then this is also an earthquake in the northern part, magnitude 4.73. Again, we see all of the models are fitting the data pretty well.
Just to make it clear, because we remove the event term, or we add the event term to the GMPE, these are more close than if you had just used the models to predict it and said, let me plug in a magnitude 4.7 at 100 kilometers, right? So by correcting them all by their appropriate event term, the models start to collapse together.
Okay. Yes.
This is probably obvious, but the event terms are based on the blue dots, basically, right? Because those are the ones that were in the NGA data set.
Yes, the event
Not
terms
included.
are from the NGA data set. Yeah.
You didn't recompute event terms considering the Arizona data.
No. And Jenny, if I misspeak, since this is your work, let me know. Okay. This is a magnitude 4.43. I'm just going to start flipping through, so if anyone sees anything interesting, please just stop me. Magnitude 4.34. 5. And then a 5.19. Okay. So next, I believe I'm going to the transition zone. So she looked at these 4 earthquakes here in this transition region. So this is magnitude 4.45. 4.26. 4.73. And this is a 4.29. So again, we're seeing that there's good agreement between the data in California and Arizona and the GMPEs. Okay, and now we're going to look at some earthquakes in this southern region. So this is the region that's crossing the Salton Trough, and we think it has a lower attenuation.
Higher.
Higher. Right. Okay. So this is the big magnitude 7.2. So there's a little more difference between the GMPEs. There's a note we need to check this.
Stop on that one.
Yeah.
So we need to look at the event term that was provided, because all the other ones look good for the Campbell and Bazorgan. That one jumps up high, although it could be the data set that you used. I'm not, but because this is one select, all of the recordings. Jenny, you used everything in there, or who? Yeah. So there's not, each of us might have had a different subset of what the recordings were, but that lower left figure shows, I think, just too big of a difference. So we need to double check that event term with you. 1 second. Because at 2 seconds, the other periods, it looks just fine. MIR 1 second event term. MIR 1 second event term.
Katie, this is Rob.
Yes?
Robin, could I ask a question?
Sure.
I'm muted. Sure.
It looks to me, you got a lot of orders of magnitude on these plots, but it looks to me like most of the red dots are below the predictions out at long distances. Is that a fair assessment?
That's true for all of them except for 1 second. There's 1, maybe 2 points above the majority of them.
Robin,
Yes.
she'll get to the mean misfit in a little bit.
Yeah.
I'm muted.
Okay, thanks.
Can I go on, or do we want to talk about this a little more? No? Okay.
You guys are going to check that, right?
Okay. Okay, so this is the magnitude 5.1 event. 4.63, and Bob, I was going to ask you, this is you and Brian. Yours is significantly higher for this one.
He said they were
Wow.
already anticipating fitting the Arizona
Well
data.
done. So are we going to check on this too?
They need to check on that
make a
one.
note of that?
So 1017.
Okay. Okay, magnitude 4.41. So the evaluation results. So provided that, given that we've done the event term adjustments, all 4 of the GMPE models are consistent with the distance attenuation we're seeing. So, and then we'll use these 4 models to feed into the salmon approach and develop our candidate models.
So this was a question for Nico. On the bottom there, is 4 enough, or do we need to do something to fill it out better?
I think we need to do something to fill the space out.
No, I mean, so this gets back to the question of creating averages. Does that help stabilize the covariance? And-
Yes, I think so.
Yeah. So we can, since the models are adequate, their averages need to be adequate, right? And we can then create a few combinations such that it just stabilizes the covariance matrix. Gabe?
Actually, this may relate to a comment I made during the working meeting a week or two ago. And I think when you're computing the covariance matrices, you should not correct for degrees of freedom in cases like these. You should divide by n, not by n minus 1 or n minus 2.
And
Among
when you
other
get,
things-
yeah, when it gets small, then that matters.
Among other
right?
things, exactly. And so your covariance matrices are positive, definite, etc. You need to do that.
Is that how you're doing it, Nico? Yes,
Okay.
thanks.
I just have a quick question. It says with the event term adjustments, all 4 candidate models are consistent with the distance attenuation in Arizona, but it did seem like a lot of the red dots were lower than the GMPEs were predicting at long distances.
Yeah, we did see that for a lot of the events, but we're going to get to that. So,
So they're consistent even though they're lower?
So how can they be both consistent and lower? They're, in our broad thing, they're not a big change in the slope. They are, you could see them coming in lower, but we'll show what the number is. It's pretty small, but it is a factor that we can correct for.
So we're looking for systematic spatial differences in the recorded ground motions for earthquakes in different places. If we fix the magnitude we ask, do things vary from place to place? But of course, the way we got the magnitude in the first place was we took a bunch of seismograms that look like these seismograms, and then we fit a GMPE through it, and we derived a magnitude from that. That's what's in the catalog. And by the way, they're different for Berkeley catalogs than Caltech catalogs because Caltech had Richter and Berkeley didn't. And so so there's spatial heterogeneity in the catalog in the first place, even if we knew what magnitude actually meant in these things. And at this level of detail, I mean, can we really, we act as if the magnitude is known in here, but actually it itself is a floating number that depends on the same seismograms that we're using in these GMPEs. I mean, it seems hopelessly hard to sort out.
Norm, do you want to?
This is not, okay. Go ahead, Norm.
The short answer is the Arizona data are not used in the magnitudes. Okay, those are TA array data that aren't part of the normal magnitude correction, and there is a small time window when those were there. In addition, if there's a magnitude error, because we corrected for the event term, all that's gone. We're just trying to see is the distance attenuation that's really based in California data from how these models were fit. Can we use that as we go to Arizona? Overall, the answer is consistent, is what Melanie said, with the caveat that there may be a shift, but it's not a factor of 2 or 3. We're going to see a 20 or 30% change, which is very tiny on those plots. So I think those are two different things. One is, are we getting the right attenuation at large distances from these? And I think the answer is yes. And it was a little surprising to me. This wasn't what we expected going in. We really were thinking with differences in Q, we would see a difference in the distance decay in California as to going in towards Arizona. Because of that, I asked Pierre several times to go back and check it again and again. And I think we can say we're very confident that the numbers are right. That all of the instrument corrections, everything has been done properly. And we've had at least 2, maybe more groups doing it separately. So, Jenny.
So I just wanted to clarify that we were testing to see if the Arizona ground motion data was higher. Sorry, we were
Yeah.
testing to see if the Arizona ground motion data was higher. Initially, that is what we were expecting, and we went through the data, I don't even know how many times. So we are rejecting that, and then Katie's going to get to why there might be a difference, but it's not because of a change in attenuation, a change in something else.
Yeah, the one comment I wanted to make is that that uncertainty in the magnitude is taken into account in the recurrence calculations. And by the way, that uncertainty is very small for modern instrumental events, but it's not ignored.
I couldn't quite hear you, Gabe. Taken into account where?
In the recurrence calculations,
Oh, on the source side.
in the
Yeah.
source side, exactly. So it's not ignored. But it turns out it's very small for modern events.
What I see still some physical inconsistency in what I just heard. Because on one side, we know that Q in Arizona is higher, which exactly means that attenuation is lower. And based on certain number of data points, you came with the conclusion that it is not the case. This is why I would like to hear the explanation. Is it some kind of magic or it's physics? And please explain this phenomena, because it is not convincing to me, or it is not convincing what is happening.
There's enough Q in the path as it's going through from the California side, as it's propagating into Arizona, that's getting you the attenuation. That's basically what we're trying to see or get at. But that, I mean, what you said was what our concept going in. The Q is higher. We ought to be seeing less attenuation, and we should see the ground motions popping up or sitting up higher. All of these events are showing the same thing. We don't see them systematically higher. I think only one event has them higher, and that was it. But you need, I mean, the Q is, the effect it needs to be all the way from the source to the site, not just the Arizona wave propagation or part of that path.
Okay, Norm, just make sure that you put this, whatever explanation you have into some documents or whatever, because it is kind of so far still against physical understanding.
Okay. So if there are no more questions on that, I'm going to switch gears a little bit and go through our approach to account for these path effects. So those are those average path terms that I showed on that first slide from the north and the south. So, wow, I have a bunch of step number ones now. I don't know how that happened. Anyway, this is just an overview of what our approach is, and I'll talk about it more in detail as I go through the remainder of the slides. But mainly, this is to get the terminology just communicated. So we're going to compute the within event residuals. Those are, well, computed by the developers, and then the between event residuals. And then we're going to use those to compute a mean site term for the full data set at those 9 stations surrounding Palo Verde. So that's going to give us our delta S to S term. And then with this, we can correct our within event residuals for the site condition. So this is the site corrected within event residual right here. And after we've done this, so this is using the full data set, step 1, 1, and 1, 1, 2, and 3, uses the full data set. And then after this, what we're going to do is we're going to take those site-corrected within event residuals and separate them into the north region and the south region. And in this analysis, the way it was originally done, and we just followed it, is the events in the transition area were included in the south. So you'll see that we have In the south region, yeah. So you'll see more events in the southern region. Then using these, we can compute our mean path term from California, the northern part of California to Arizona, and then a mean path term from the southern part of California to Arizona. And we'll compute our mean source term as well, so the mean event term. And then we can estimate the epistemic uncertainty in these mean path and source terms. Okay, so that's the notation, and now I'll go through our procedure to do that. Now, Linda's going to be talking about this for, I think, more than an hour this afternoon, but I've just included this slide. I think probably everyone in this room has already seen it, but again, it's just to make sure we have the terminology straight. So this is our residual. It's a combination of our between event term for each earthquake and our within event term at station S for earthquake E. And then our total sigma is a combination of our between event and our within event standard deviation. Okay, so this is a plot of the within event residuals at those 9 stations surrounding Palo Verde. So we have 14 earthquakes in our data set, and they're color-coded by earthquake in this plot. So this is at 0.5 seconds. And then these are the residuals within event residuals at 2 seconds. So on all the plots, I'll show 0.5 seconds and 2 seconds. Okay, these are the event terms for Chu and Young's. We still need to pull them out for the other ones, but I'm just going to use Chu and Young's as the example here. So these are the event terms at 0.5 seconds, 1 second, and 2 seconds. And they did not include this particular earthquake in their model. Okay, so if you average those event terms for the different periods, dividing the data set into the north, the transition zone, the south, and then also average them as a combined total data set, there's really no statistical difference between the regions. But so the idea is we want to use the combined term to separate it out from the global average. So we can get the difference from the difference from the average global model can be resolved. And just one note, this came out of a discussion we were having with Jenny the other day, or yesterday. For the event terms, only those 9 stations, right, Jenny, surrounding Palo Verde were used. Only earthquakes recorded at those 9 stations were used for the event terms. And what she pointed out is what we really should be doing is use a larger data set to get at these event terms. So I think we need to do that.
There are other earthquakes that were in the GMPEs in those regions, but were not recorded by the TA array. And so for this part, we can use a broader set, and we need to expand that to all of the available earthquakes.
Okay. Okay, so this just shows the 9 stations that we're using. And then the plots that follow, I'm going to show the delta S to S term here. This is how we compute the delta S to S from our within event residuals. And I'll show some plots of the earthquakes recorded at this station closest to Palo Verde and an estimate of our delta S to S term. So these are the within event residuals at that particular station. And this is the estimate here, this black line, of our delta S to S term. This is at 0.5 seconds.
We do see there a slope, right? And that's one of the issues. So right now we're just taking out an average, but there's an indication that that one has a slope to it at the larger distances. You saw that earlier in Katie's plots when she put them all together. Beyond 500, these things are starting to turn up. That would be the low or the high Q finally being able to exert itself. So I think we're going to have to look at truncating that, maybe chopping those off at 500 or 550 or something like that.
Okay, so this was 0.5 seconds. And then this is 2 seconds. And this just shows our estimate of that delta S to S term for each of the 9 stations. The station in blue is that station near Palo Verde that I just showed. And then in red at the bottom is the mean then for each period. So the mean delta S to S term.
So before you go on to answer Robin's and Melanie's question, it looked like there was a systematic bias. These are on average are negative, and the event terms on average were negative, right, when we rederive them. So you're seeing or looking at this part would say we should be lower than the curves by 20 or 30, 20% say. The other part said when we do the prediction, it should be lower too, right? Because the event terms are lower in that part of the state than our worldwide model. So those are 2 separate parts of the model. We only would have seen this one in the plot she ran through because she had taken out the event terms previously, right? They were centered on this.
Okay.
So this would say for these sites, the event term wasn't quite getting us to the mean for the Arizona data. But it's a
Small.
yeah, 10 to 30%.
Yeah. Okay. All right. So the next step then is to compute site corrected within event residuals. So we're simply going to subtract that delta S to S term off of the within event residual. So
And just repeating, Katie, here you see 500, the upturn, right? So we probably need to really chop that piece off and treat it differently because our sources are generally not that far away. The controlling ones are out to 400.
2 to 400, right? 200 to 400 is what we care about?
The delta S2S term that you're subtracting, is that average over all 9 sites or the one for each site individually?
For each site individually. So that's been done, and then this is just a plot of the site corrected within event residual. 0.5 seconds, and then at 2 seconds. So they're centered around 0. This is good. Okay. Okay, so now we're going to separate them. So that was everything we've done so far is using the full data set, north and south combined. So now we're going to break it apart, and we're going to look at the northern region and the southern region separately. And the earthquakes in the transition zone are included with the south. Okay. So this is our dividing line at this point in time. So northern region, southern region. Okay, so the plot on the left shows then the site corrected within event residual for 0.5 seconds in the north. And then the blue dots on the left, these are the residuals for the south at 0.5 seconds. Okay. And then these are the residuals at 2 seconds. And now if we can compute our average path term for the northern region to our target area on the left, and then our southern region to our target area, California to Arizona. There you go. The southern path from California to Arizona here is on the right, and the northern path from California to Arizona is on the left. And the dark line indicates our estimate of these path terms for the north and the south, respectively. And this is 0.5 seconds and 2 seconds. And then the final step is just to estimate the epistemic uncertainty in our path terms. So this is how we're computing that. And then this table shows then our phi terms, our path terms, and then the standard error, which is the epistemic uncertainty for all the different periods. And then the top table is for the north, and the bottom table is then for the south.
Hi, Katie. I just have a quick question. I think I missed it. The S to S term, the S to S term that was estimated. I take it that was estimated with random effects, or the average. On average, how many recordings were? 5 was the minimum. Okay.
Yeah.
Thank you.
So in any station that didn't have 5 recordings, we didn't compute an S to S term for. All right, so again, this is a picture of the logic tree that Bob talked about this morning, and this is the,
Katie?
yes?
Can you go back to that table?
Yes, this one?
Yeah, kind of explain, sort of summarize what we're seeing here again.
Sorry, I went through that kind of quickly. So
I
this
can't
is,
say that I totally followed everything that, where we got here. You know, maybe it was too fast or I'm just too slow, but.
so this is our fee term. Okay. Yep. So p hat. Here's how we derive that. This is then our site corrected within event residual. It's an average site corrected within event residual for the north, which is our p hat term. And then this is our site corrected within event residual for the south. So that's our p hat south term. So these are our path terms. Okay, and then
Let's go slow, just so, is that part okay, Ken? That would be the constant that's added to the GMPE for sources coming from the north into Arizona, and a different constant is added for sources that come from the south. So now we're distinguishing the azimuth of the waves that are coming in and saying the attenuation is different. So we talk about this being a single path. So her north ones are coming in higher, positive in this case, and her south ones are coming in negative, meaning lower amplitudes from earthquakes that have propagated from the south into Arizona compared to ones that have propagated from the north into Arizona.
which is kind of opposite what we would have
No, that's,
thought, right?
if we have higher attenuation going
Okay.
through the Salton Trough, that's the direction that we expect it to be.
Okay.
Tom?
Yeah, I was just going to say that it would have helped if those have not only been the same scale, but they zeros have been co-located. Because I don't know if people can see the numbers in the back, but
Okay.
those are radically different scales.
Okay. Good point. Thank you.
Yes, so one looks higher than the other, but it's actually lower, right, is the,
Yeah, by a lot.
Yeah. So this is
on the
actually,
left, the scale goes up to 1.4.
this line is like at 0.21 or 22, and then this line is at minus point,
two. or
probably
something,
2.
yeah.
So,
And the ranges are quite different, too.
right.
We need to fix the plots that have common axes on the y.
You know, they looked pretty good at 2 a.m.
So you're doing this to recenter so you're taking the residuals and recentering them, and that's how you're getting this pattern, right?
We're getting an average residual first of all.
Right.
For all of the sources.
Right.
Combining them all, right?
Yes.
By taking out we center on the site term, and if you take out 9 different site terms, and they're individually centered, then together they must be centered on 0, right?
Right. Okay.
Okay, now we break that
Overall,
out.
yes.
Overall.
Yeah.
Now she's going to break it up into 2 groups.
Yeah, okay.
One from the north and one from the south,
Right.
and they're no longer both at
Centered
0.
on- yeah.
One's
Yeah.
higher and one is lower.
Okay.
Yeah.
so-
And we're now postulating that this is a systematic effect
Right.
that we will see in future earthquakes.
Okay.
Or you could say, no, there is no systematic difference. You can't resolve this. All right?
Yeah.
And so the next plot or the table was those numbers in the middle. That would be the constant that you add to the GMPE, the p hat. Okay, so it's another
To,
term that's
to
added
center
on.
the residual, yeah, okay.
So use that, say if it's coming from the north, I'm going to add 0.42
So
to the
system-
half second. If it's coming from the south, I'm going to subtract minus 0.27.
Question? Are you going to redo this from 200 to 400 kilometers if that's the zone that we care about? Is it really not much different? Because it looked pretty different from the last slide.
Yeah.
I'm trying to find the.
So the reason why those numbers are a little different, I did the ones in the table, and they're just 200 to 400.
No, I mean,
but
go to the one where it's split up into the north and the south. The next one, I guess, where you were calculating the key.
Yeah, there's not much data from 2 to 400. Yeah.
But the data which are there are systematically different. You need to use the microphone.
The uncertainty will be huge.
We can do it, but the uncertainty will be significantly larger.
We
May
could-
I ask a question? I'm sorry, I'm having a little hard time understanding the rationale why the transition zone was associated with the southern path and not the northern part. What was the rationale and what is the consistency moving forward in the hazard calculation?
I can tell you the second part, and maybe Jenny can answer the first part. The event terms there were not any different, so that part doesn't make a difference. And now it's on the site terms, if you can tell the difference.
So it's not really a transition zone. The zone in the middle, the paths are approximately going through the Salton Trough. The geologic-
Try to like.
Sorry, I don't
be
want to give everybody my cold who uses this after me. So the section in the middle, the paths are going through the geologic area that's called the Salton Trough. So those were sort of harder to pick out, whereas what I called the south was much easier to pick out because you can see the Gulf of California on there. So I would just say the central zone is not a transition zone. It's going through the extensional zone, but maybe where that northernmost line should be, we might want to shift a little bit in the future. That was all.
But your point is, it's basically taking a more similar path than it's going through similar geologic unit
To the
as.
southern.
Yeah. Okay.
So getting back to that table, so I understand the path part, and the fee part is the single, was that single station fee or just?
This is path to region. Linda, do you want to talk about this a little bit?
Oh, it's single station and path?
Well, it's not really, because we're talking about a region now around Palo Verde. So I'll let.
Yeah.
So it's not single path fee in the classic sense of single path, like it's more like similar path fee. So all the earthquakes are located in one region and the site is in another region, and these paths are similar. That's what we're saying. And
Okay, all right.
Yeah, but normally we've used the word single path to go from a region, source region to a site.
Yeah.
Right.
Now we're going to have 9 sites, and we're averaging that effect over
Yeah,
all 9
yeah,
because
okay.
none of them
All right.
are the exact
But
power
the
plants.
concept is
Same concept.
is similar.
Yeah.
Okay.
It's-
And so that fee was gotten by your first approach, the first centering before you split out the two things, or is it?
yes, so first we take out the site terms at each site, then we split the data set into north and south, and we take out the systematic path term from each set of site-corrected residuals, and then get the standard deviation.
And this is
So
after removing 2 things.
Yeah, okay.
You're going to take the normal within event residual, you're going to subtract out the site term, the delta S2S, at each one.
Okay.
And then all the ones in the north, you're going to subtract out that northern term. All the ones in the south, you're going to subtract
okay.
out the
All right.
southern
So the
term.
fee is done after the correction
Correct.
for the okay,
Yeah.
that's where I
Yeah.
was. Now I understand these numbers.
Yeah, and I will explain it another time also in my presentation.
you'll hear this all again this afternoon, the second time when she's focusing on fees.
So why don't you guys call that a region term instead of a path? Because it's not really a path. It means that the path is contained within that region.
I, for
If
the
we-
record, agree with you, Christine.
Thank you.
But it's a wave propagation term, so I need to call it something, and we usually say path for wave propagation.
Yeah, and
Yes,
usually
but
we use
path means this. It took so long to get people to understand what single path is.
Yeah.
Single
We-
region.
We are open to a new term here if you can find the one that works. So
But Christine,
Path
usually
region.
we use this. The region is for event terms, so it's kind of confusing.
Yes. Okay, but can we find another term so people
Single
finally
path light.
understand? Yes. Single. Combined path, grouped path.
that's why there's a dash R there, single path to a region.
Okay.
That's what it says.
Yes. But don't
I
call
thought
it the
this was
single
good.
path.
Yeah.
I agree with you, Chris. We've been struggling because it's, how do you not make it too wordy?
What about similar path instead of single path?
Yeah, we need a word that's
Similar.
means similar that doesn't start with an S.
Analogous. Okay, another question. If there was something systematic in the source, say stress drop, it would probably map into the p hat, right? Or will it stay in tau?
Something systematic in the source?
In the source, regionally systematic, north versus south.
Oh, because yeah, we used a combined data set to remove the source.
So we would
So-
argue that when we looked at the event
getting-
terms, which if we treat that as the source and saw no systematic difference between the north and south event terms, that that's not what's going on.
Okay.
That it is the wave propagation difference.
All right.
Right? Because we did, that's the table she showed earlier where the standard errors were so big you couldn't tell any of them were different.
Okay.
Okay. I guess I'll just put up the logic tree and how we've broken down that term that branch that Bob showed. So in the logic tree that he showed this morning, this is then the combined path and source terms. So we've combined all these effects into one branch of the logic tree. So this is basically what goes into this combined branch of the logic tree. So then this is our mean delta S to S. So this is the average now of all 9 stations here on this first branch. So either that's the same as California or it's not. That's the first branch. And then we have our between event residual. So this is our source term. So we have our source term for the northern region and for the southern region. So either we use a global average or a source specific or a source region specific between event term. You look like you want to say something.
Yeah, so let's go slowly here. So let's
I
start.
must be running out of time though.
No, you have 20 minutes, and I want to make sure you need to know what we're saying on the structure here, right? On the left, she has 2 branches. So let's start with the delta S2S. So the top one means we're going to assume that the average was really 0, and our small sample is even though we got a non-zero difference, it's not robust. We're going to say it was really 0. Okay? And so then we would, our standard deviation would bump back up again, right, in that case. The mean delta S2S, otherwise we're going to use those estimates that you just saw. Okay? So that's causing a constant shift of 20%, or we were saying, right, between the generic model and then the application of that model to Arizona. And Gabe, that would be where we can't tell you what's going on there, whether it's the site or whether the sources never generated them. That's exactly the same thing. So there's a complete trade-off and we're stuck. So we don't attribute it to where it is, we just say there could be a constant shift. Then the second one that she's showing,
These are our event
yeah,
terms.
so event terms. So global average means what?
What, it's just the average from the
Which
California,
is,
basically, is what we're
right.
using.
But the global average of the event terms is
0.
0, right? So that would mean that difference, we're going to say again, is actually 0. It's not robust, and we're going to assume they're all the same. The lower one is we would use the average term that we calculated. Okay? We have north and south. What we just saw previously, north and south aren't different enough. Really, those are going to be collapsed into one tree. Okay? So she's got it as 2 trees here, but we're going to just have one. Either global average, or we see a systematic difference with lower ground motions coming from this part of California as opposed to the rest of the world. Clear? The next one?
There is no next one.
Path term.
Oh, I thought you meant next slide. I'm like, there is no next slide. This is my last slide. And then this is the path term that we just talked about. And then what we would be putting here is then the uncertainty, the statistical uncertainty that we were showing in those previous tables for these branches. And so then we would have one branch for the north and one branch for the south to represent that systematic path.
What we don't have right now is a 0, and maybe we need a 0 line on there that there is no path.
A no path?
There's
Oh,
no
oh.
adjustment.
Yeah, like right, like in between here. No adjustment.
Yeah, no adjustment.
So Norm, I have a question. I know what we're doing, but in the forward application you're showing here, you are applying to your site the mean S to S. I am not very sure about that. I mean, is there going to be site-specific study?
Yeah, but that's not what, so if you apply the mean S to S here, it's not as a site term, it's saying this is a source term. This is, when we compare our predictions to Arizona, they are systematically high.
Just the bias, basically.
It's the bias, and we can't tell where that bias came from.
But downstream there will be a site response.
Correct.
Study. Okay.
So it's really not trying to find the bias in the site, it's trying to find an overall bias, and either we believe that we can tell, or we don't. Does that make sense?
No. Oh, Katie.
Yep.
And Norm. I have a question. So the data that you use to characterize the source term and the path term are mainly small magnitude earthquakes.
Yeah, we used, well, I'll show you the data set we used.
Yeah, except for Kukubai.
There are 50 slides, so. There we go. This is what was used. These are at least the events.
So basically, you're assuming that the source term doesn't have magnitude scaling in it. Right? That what you get for the smaller magnitude will also apply to the larger magnitude. That's your assumption.
Mm-hmm. There is that one magnitude 7 event, but yeah.
As Katie, as we talked about this morning, or sometime in a few last 15, 20 minutes, there are more events to look at than just the events that are recorded in the TA array, that are in our data sets, that are bigger, that are bigger than the ones that are recorded in terms of attenuation, to look at the source terms in NGA from the bigger events that are in this region.
Yeah.
But so that we have to look and see whether there is any systematic difference in different magnitude intervals that we need to account for. That is a good point, that we can't just rely on magnitude 4s to predict differences in sources of magnitude 8.
Adrian?
Maybe, can you go back to the last slide, please?
Maybe it's easier to, here we go.
You have a branch for a source term, and you have another branch for a path term. How do you, did you have enough data to make sure that the two branches are not correlated?
Did we have enough data to make sure the two branches are?
Not correlated.
I think there is a correlation between the branches. The effect could really go either place, right? I mean, do you want to comment on that, Norm? You're shaking your head. But
Yes, you're right. They're likely correlated. We can't tell that one on the first. There's a delta S2S and a average delta B, right? Those are completely correlated. There's no possible way to separate the two.
And you're going to build that correlation into your choice of weights, no?
Because all we're going to do is we're not putting ranges on there. We're just getting means. So the sum of, I don't have to worry about correlations when I'm just going to add the two numbers together. If I was tracking the uncertainties and variances, then I'd have to deal with correlation. But all that's happening here is the mean is either 0 or non-zero. That's what our model is right now. If we make all those non-zero, we're addressing somewhat what Brian had said. This may not apply to magnitude 8s. This might only be a difference in the source characteristics in magnitude 4s. And that would be our branch where there is no change. But correlation isn't here. Does that make sense, Adrian? That because all we're using is a mean value. And so I can add two numbers and not worry about correlation. When we go to the path term there, I should be uncorrelated because all of those things are stripped off, right? It's measured after taking them away. Ken, did you have something?
Just a clarification. So the combined effect, north-south, that would just combine those two branches that are north and south? Or the entire
No, it
logic?
would.
all of this.
It would basically, we would be convolving all the uncertainties we
okay.
see on the left into a simple representation by three.
Then the correlation doesn't even, I mean, I know it's not a factor anyway here, but now it's not even an issue.
Yeah, it doesn't matter where you account for it, right?
Yeah, now, because
So
it's
we-
all one big
Yeah.
effect.
It's all basically one effect that we scale off of from the California models, adjusting for differences in the possible source or path effects that we basically end up being just some scalar parameters that shift the models up and down because the distance range is pretty narrow for the implementation case. We're not doing hazard from sources from 100 to 600 kilometers. We're doing hazard from big earthquakes at a relatively narrow distance range.
We want to keep a reasonable number of models and keep it from blowing up. So that's simply to take what might be 10 or 12 or something and collapse it into 3. Is that all good? I think you're all.
I think I'm finished.
Anything
so.
else for Katie? So this is, when you have data, you can start to do something, right? As opposed to just saying, I'm going to grab the global model and apply it. So now we can start to deal with specific ways of what we think the ground motions are from these California big events coming into Arizona. That's really the whole concept here.
Okay.
Add one more question. Will you have epistemic uncertainties on those terms? The side term, so you basically thinking that is a precise estimates of the side
So
terms?
right now, the plan is no, and it's going to come back. We need to see again, looking at the hazard, if it really matters or not. But our epistemic uncertainty is 0 or it exists. If it exists, we're not then putting multiple options of what it is. So that we're just doing the two pieces of it. If that doesn't make a large effect, then we're not going to go refine refine to have three different values if it exists. If it does make a big effect, then we have to go back and bring that branch along. Then we get into the correlation issues that Adrian had talked about as well.
Okay.
I think we're 5 minutes ahead, even more. So let's stop, and then is lunch ready? Any questions for Nico from yesterday that you want to ask? Nico's not going to continue today. Nico will be doing Diablo Canyon Strike Slip tomorrow. So we'll go through that in the same way. I'm expecting it'll be, well, the difference is we're going to now bring in the simulations. And what do you do with those, right? So Nico was just starting to show you that yesterday. Yeah, that's okay though. That's what all this has been.